So students, welcome back. We were looking at nuclear reactions and we were particularly looking at the various types of nuclear reactions, and we'll continue with our discussion. So we had seen the different types like this up to elastic scattering. So in elastic scattering, then disintegration. Disintegration is this type of a reaction that I have just written it here. So this is the disintegration reaction, and in disintegration, on striking the target nucleus, this is the target nucleus with an incident particle, then what happens? The incident particle gets absorbed and a different particle is comes out. So it is like this. You see, this gets absorbed in this. Actually there is to be an intermediate step out here. The intermediate step would be just like this. It would be 18x9, where x is that element whose atomic number is 18. So after that, what happens? Since this will be in an excited state, because all of them are not in a ground state, so it will be an excited state and it will emit this, and this one will become this. So this is a disintegration type of reaction. So this is done with. Then here I think probably I had written here radioactive capture, which is wrong. It should be radiative capture. In the part A I had of my lecture, I had written radioactive capture. So please take care of that. This is radioactive capture. So in radioactive capture, what happens is that again here you see this gets captured, so that we get this one. And students, you must remember that this intermediate step is called the compound nucleus. And the compound nucleus rarely stays like this. There are very rare cases where it stays like this. After that, it's break up into another element like this. You see, it is just so easy. 26 plus 1 is 27 out here, and 12 plus 1 is 13 out here, which is in an excited state. And why it's an excited state we'll come to know when we do the compound nucleus theory. And then this breaks up like this. So this is like this, and it's called radioactive capture because this is radiation. Here what happens is that in this case, you see, this is not a particle. It is not following x plus x going to y plus y. Here instead of y we have a particle, that is a gamma photon, and so it emits a radiation, that is radioactive capture. So when the reaction is such that the product particle is not a particle but a gamma photon in that case, but in the quantum mechanical sense, a gamma photon can also be called to be a particle, said to be a particle. So that is radioactive capture. And then we come to direct reactions. What are direct reactions? In direct reaction, there is no such intermediate step like this. There is nothing to be here. So directly this reacts with this, and this one picks a part of this. So what it happens is takes one of the protons, so that this becomes not the protons, the copper, one of the neutrons. Can you see here the number of proton is 24, it remains 24. So it is copper and it remains copper. But what happens is that the mass number increases, because as you know, on the top what we write is the mass number out here. So if I have got an element like this x, here we write the mass number. And what is the mass number? It is the sum of the protons and the neutrons. And here in the base we write the number of protons. So this is A. So it becomes an isotope of copper like this, and with the emission of this, and we will see that this is nothing but a proton, 1H1. So that is a direct reaction. And under direct reaction there are two types of reactions, which direct reaction has got two types. A, is pick-up reaction. Pick-up reaction, in which what happens is the pick-up reaction, and then the other is a stripping reaction. Stripping reaction. So we will remember pick-up and stripping. In this is a pick-up reaction, because you see here what is happening is that the target nucleus picks up a neutron from here and it becomes a product nucleus. And this reaction, if it proceeds in this way, it becomes a stripping reaction, because you see what happens here. This is 64 copper with a mass number of 64, and as a result of this action with alpha particle, this plus this gives us 63, copper 63, which is one neutron less than, so one neutron, it has been stripped off of one neutron. It is as if this one hits this, takes one neutron, and it becomes like this. That is what is meant by stripping. So that is direct reactions. And number 6, we have photo disintegration. So what is photo disintegration? You see, photo disintegration is it is like just the opposite of the radioactive capture. In radioactive capture, a gamma is emitted. A particle hits the element, the target nucleus, and as a result we get a gamma photon. Here what is happening? Here a gamma photon reacts with a nucleus, so that we have a neutron, which is a particle, as a product. So that is photo disintegration. And then spontaneous disintegration is nothing but alpha and beta decay. We'll look at it some when we do induced radioactivity. You do not have spontaneous radioactivity in your syllabus, so we'll do induced radioactivity, and we'll take a look at beta and gamma decay. And then this is spallation reaction. And what is spallation reaction? In spallation reaction, look at this. We have a uranium, which is a very heavy nucleus. Its mass number is 235. That means, and look at this, 92. Number of protons is 92. Sum of the number of proton and neutron is 235. It has been hit by a neutron, and as a result I have this and this, and 2 neutrons. So in spallation reaction, under spallation reaction we have nuclear fusion also. This is like a nuclear fission, because uranium has broken up into 2 parts which are quite big, and we have also a number of particles, and sometimes it will break into only one big nucleus and a number of particles. So this is in short different types of reactions, but there may be 2 or 3 more which I'll be sharing in the Google Classroom, and you need to know about them. Now we go to the conservation laws satisfied by nuclear reactions. So conservation. So these are laws that has to be satisfied by nuclear reaction. Conservation laws. You should know these are conservation laws for nuclear reactions. Okay. See, first of all, we have those conservation of energy, momentum. We have momentum. Then we have, this is linear momentum. Then we have angular momentum. Angular momentum. charge, these things are common. And then now conservation of energy is not a requirement for all nuclear reactions. It may be in some, but this has to be satisfied in elastic collision. Then in inelastic collision, energy may not be conserved, but momentum has to be conserved. Now these things are there. Now look at this. There are certain things like the conservation of charge. Charge means actually we talk about the conservation of the number of protons, because you see when I have like this x plus x is equal to y plus y. Now if this has got a atomic number z, and suppose this is z minus 1, and if this one is a proton, then this has to be, you see, this becomes z plus z. You have got z number of protons here, you have got one number of proton here, but here you have z minus 2. So this element must be something where the protons, there are two number of protons. So things are like that actually. Or if it is x plus x, then I get here y. Suppose this is z and this is also z. In that case, what will happen? In that case, you see, or this is suppose if this is z and this is a proton, in that case this particle must not have a proton, otherwise, sorry, this must have one proton, otherwise z, and from here one more z, so it will be here z plus 1, and this is also z plus 1. So this number has to be satisfied. And another thing is that the nucleon number, that means the number of neutrons on this side, the neutrons plus protons on this side must be equal to the neutrons plus proton on that side. That means A on this side must be equal to the A on that side. Then these are certain things that are quite simple, but then there are certain things like conservation of parity. We have talked about parity in the first unit. So we have conservation of parity, conservation of isospin. We have also talked about isospin in our first unit. And then something I have forgotten to mention, I should have mentioned in the beginning, conservation of spin. So what is conservation of spins actually? Actually, in conservation of charges, I forgot to tell you that if I have got a, you see the charges, we have the proton and the neutron. So in that case, what happens is, sorry, neutron is chargeless, so I have the proton and the electron. So if you have a electron that side, then again this is equivalent to a negative charge. So in case of electrons, a proton can be written as like this, 1, 1 like this, and the electron can be written as -1 and 0 out here. Why? Because when I write something like this, an element, here we write the number of protons, and here we write the sum of number of protons plus neutrons. So we'll talk about this in the part C of today's lecture.